The state of Meghalaya in northeastern India is one of the wettest places on Earth. During the monsoon season, the sheer volume of water moving through these valleys is almost difficult to comprehend. For standard civil engineering, this extreme environment is a nightmare. Torrential rains consistently strip away topsoil, undermine deep foundations, and expose steel rebar to rapid oxidation. Rigid materials like concrete cannot adapt to constant moisture and shifting earth. Eventually, the structural integrity gives way, and standard bridges snap under the immense pressure. This graph maps structural integrity over time, illustrating the core problem. Conventional infrastructure relies on dead materials. A concrete bridge is at its absolute strongest on the very first day it opens. From that moment on, it is constantly degrading. Centuries ago, the indigenous Khasi and Jaintia communities faced this exact environmental hurdle. They solved it by discarding conventional construction rules entirely. Instead of pouring concrete, they grow their infrastructure. These are the age&heals, or living root bridges. When we add a root bridge to this same chart, the line moves in the opposite direction. It begins with zero capacity, then gains strength year after year as the living tissue thickens and fuses. The foundation of this system is the Ficus elastica, commonly known as the Indian rubber tree. This specific species has an exceptionally fast growth rate. More importantly for construction, it produces hundreds of thick, pliable aerial roots that hang directly from its upper trunk. Left alone, these roots drop straight down into the soil. The engineering begins when builders intercept them, directing the living wood horizontally across a river or a deep gorge. To guide the growth, builders construct temporary scaffolding. They hollow out betel nut trunks or bamboo poles, threading the young roots through the tubes to physically bridge the gap. Establishing these primary horizontal spans requires multi-generational patience. It takes 15 to 30 years of careful maintenance by the community to cross the gap securely. By training the tree's offshoots in this way, the builders force a chaotic, vertical biological process into a deliberate horizontal structural foundation. But a loose bundle of roots cannot carry heavy loads. To achieve high tensile strength, the system relies on a botanical phenomenon called inosculation. This illustrates inosculation. When secondary roots make contact under pressure, they physically fuse. Looking closer, the bark on touching surfaces degrades, and internal vascular tissues merge. Separate living strands combine into a shared biological unit. If you weld a steel bridge, that joint is static and eventually rusts. This living weld is a continuous, active process that constantly deposits new wood to reinforce the connection over time. Over decades, inosculation transforms thousands of fragile, independent root tendrils into a monolithic, load-bearing truss system. As the bridge matures between its 15th and 30th year, it demonstrates a sophisticated engineering trait, adaptive load-bearing. Under mechanical stress like tension or compression, living wood biologically responds. The tree actively adds mass, thickening the wood exactly where physical strain is highest. The builders also wedge heavy stones into the gaps to create flat walkways. The roots sense this added pressure, grow around the stones, and lock them permanently into the structure. While a young span safely carries just 2 or 3 people, a mature root bridge thickens until it can easily support the weight of 50 people crossing at the same time. A concrete pillar microfractures under heavy, repeated loads. The living root bridge actively detects that identical stress and biologically manufactures extra reinforcement to handle it. The resulting gap in operational lifespans is massive. Modern concrete infrastructure in this region often requires replacement in a few decades. A well-maintained living root bridge can safely cross a river for over 500 years. Beyond transportation, these mature spans function as highly efficient, carbon-negative infrastructure. Because it is a living organism, the bridge actively sequesters atmospheric carbon, purifies local water runoff, and lowers the ambient temperature of the air around it. The structures also provide critical ground stability. Their vast root networks spread out along the riverbanks, deeply anchoring the soil and preventing the soil erosion that washes standard bridges away. A mature age&heals tree outgrows its original purpose. It transitions from civil engineering into a keystone biological organ that sustains the local tropical ecosystem. This ancient indigenous practice points directly toward an emergent architectural discipline known as biobotanic, or building botany. Inspired by the Khasi and Jaintia bridges, researchers are testing ways to weave living plant systems into modern urban structures. These projects borrow the core mechanics of root fusion and adaptive growth to cool cities and stabilize metropolitan ground, using the tree's natural self-repairing properties to mitigate the heat generated by concrete-heavy neighborhoods. The bridges of Meghalaya suggest that our infrastructure doesn't have to be a static liability. By adopting these bioengineering principles, we can design cities that function like living systems, growing more resilient and more integrated into their environment with every passing century.
Welcome to This Explainer. Today, we're diving into something absolutely mind-blowing. We're talking about a 500-year-old indigenous bioengineering marvel from India that is literally rethinking how we build things. It's a method that consistently outlasts modern infrastructure. And, as we search for sustainable solutions today, this ancient blueprint completely challenges everything we think we know about construction, durability, and our relationship with the natural world. I mean, think about the multi-million-dollar headaches modern civil engineers face, right? They're constantly battling rust, decay, erosion. Now, imagine if the solution wasn't some newly invented super material cooked up in a lab, but a profound collaboration with nature that's been perfected over centuries. So what if infrastructure actually got stronger with rain? It's a beautifully provocative question, isn't it? Because in modern civil engineering, extreme weather and tropical monsoons are pretty much the ultimate enemies of our structures. Water washes away soils, it induces microcracking in concrete, and just aggressively degrades our materials. We spend billions globally fighting the elements, pouring concrete, patching washed-out roads. But imagine if, instead of battling nature in this endless, super expensive war of attrition, our infrastructure was actually nourished by it. What if the very thing that usually destroys our bridges was the exact fuel needed to make them indestructible?
Section 1. The infrastructure problem.
This stark contrast completely flips our whole engineering paradigm. Think about standard infrastructure for a second: steel and concrete. These are supposed to be our strongest materials, right? Yet they have a definite, unforgiving expiration date. They decay, rust, and crack under extreme tropical monsoons, which means they need constant, really expensive maintenance just to keep them safe. Now contrast that with the living alternative. Plant roots actually thrive in the heaviest rain. They self-repair minor damage through continuous biological growth. They grow progressively thicker and stronger with age and moisture, all while actively pulling carbon out of the atmosphere. It's an incredibly elegant inversion. While our toughest human-made materials are slowly destroyed by their environment, this living alternative is actually being constantly upgraded by it.
Section 2. The living bridge solution.
To see this solution in spectacular action, we're going to travel to the subtropical region of Meghalaya, India, which is home to the incredible living root bridges, known locally as Jing Kiing Dri. And here's the crazy part. These stunning bridges aren't built, they are entirely grown. The indigenous Khasi and Jaintia communities masterfully guide the pliable aerial roots of Ficus elastica, the Indian rubber tree. This specific tree is an absolute bioengineering goldmine. Why? Because of its rapid growth rate and its really unique ability to produce incredibly strong, abundant aerial roots in extreme humidity. The indigenous communities recognized this botanical superpower ages ago. Rather than chopping the wood to build a static structure, they harness the living organism itself to grow dynamic, self-sustaining pathways over raging rivers.
Section 3. The botanical blueprints.
Okay, so the crucial mechanism at play here is this fascinating biological process called inosculation. You can think of it as basically nature's welding. When the secondary roots of the rubber tree touch each other, they don't just get tangled up like a messy ball of yarn. They naturally anastomose, or fuse together. They literally meld into a single integrated biological circulatory system, sharing water and nutrients. Over decades, this natural welding forms the complex, heavy-duty trusses, suspension cables, and handrails of the bridge. It's essentially 3D printing, but with live organic material, where the individual strands merge into a completely unified, load-bearing monolith. The actual construction process is an incredibly deliberate, step-by-step collaboration with nature. First up, the communities direct young, pliable aerial roots horizontally across a gorge. They often use temporary scaffolds like hollowed-out betel nut trunks or bamboo to act as guides. Then, as these roots grow across the expanse and make contact with one another, they readily fuse together. Next, to shape a flat and walkable surface, heavy stones are carefully slotted into the gaps of this root network. Finally, as the roots mature over the years, they thicken into massive woody trunks, literally wrapping around and swallowing those stones, locking them securely in place to create a perfectly stable, incredibly dense walking path. Honestly, it's an engineering marvel that happens entirely in slow motion. Section 4. Decades of indigenous engineering. Unlike modern infrastructure that we generally demand to have built and fully operational in a matter of months, growing a root bridge is a profound generational relay race. Year one is really just about initiating and carefully guiding the young roots. It actually takes a full 15 to 30 years for the bridge to achieve functional maturity and true structural soundness. Think about that for a second. This means the person who begins growing a bridge is often doing it entirely for their children and grandchildren to use. It is a stunning display of long-term thinking. But the payoff for that incredible patience is just staggering. A lifespan exceeding half a millennium. With active, mindful maintenance from the community, these living structures can endure for well over 500 years. And the true secret to that 500-year lifespan is biological adaptation. Because the bridge is a living organism, it actively responds to its environment and the forces placed upon it. Actually, it's a lot like how human muscle gets stronger with exercise. When a young bridge first forms, it might only be able to safely support a handful of people. But as it repeatedly receives a heavy load from foot traffic or high winds, the living wood dynamically adapts to the mechanical stress. It actively strengthens itself under both tension and compression, layering more wood in the exact places where the strain is highest. It literally becomes more resilient with every single person that crosses it. To put that remarkable structural resilience into perspective, a single mature living root bridge can safely support the load of more than 50 people at once. Just let that sink in. A bridge grown entirely from tree roots, originally guided across a roaring river by hollowed-out pieces of bamboo, can hold the weight of 50 adults suspended in midair. No way, right? But it's true. It is an absolute masterclass in high tensile strength and adaptive node-bearing. Our modern steel suspension bridges require teams of inspectors and million-dollar budgets to maintain safety standards, while this tree just quietly keeps doing the math and adding strength exactly where it's needed. Section 5. Inspiring future cities. So how do we pull this vital lesson into our modern urban designs? Well, the benefits of this indigenous approach extend way beyond just getting us dryly across a gorge. Throughout their operational lives, these bridges provide incredible socio-ecological resilience. Think of this as the ultimate checklist of everything our modern concrete cities desperately need right now. For starters, they act as completely carbon-negative infrastructure, actively sequestering CO2 from the atmosphere while we use them. They also prevent regional soil erosion, purify water runoff, actively cool their localized environments, and serve as a keystone habitat for crucial forest biodiversity. A multi-million-dollar concrete overpass does absolutely none of this. But a living root bridge, it does all of it just by existing.
Now, this ancient indigenous knowledge is actually becoming the foundation for a fascinating modern application called biobotanic, literally translating to building botany. It's a modern architectural movement led by visionary researchers like Ferdinand Ludwig. And the goal here isn't just to slap a few potted plants on a balcony or build a green roof. The vision is to integrate living plants directly into the load-bearing structures of urban environments. Picture this: multi-story buildings where the structural columns are living, growing tree trunks, interwoven with steel walkways and living canopies that provide natural shade. By taking direct inspiration from the root bridges of Meghalaya, architects are exploring how this kind of living architecture can actively combat urban heat islands and offset the severe impacts of climate change right in the dead center of our concrete jungles. I want to leave you with this final, provocative thought. If we can grow bridges in the rainforest that consistently outlast our toughest concrete, how will we grow the cities of our future? The Kasi and Jaintia communities have proven, beyond a shadow of a doubt, that it is entirely possible to intelligently collaborate with nature, rather than constantly trying to pave over and dominate it. So look around your own built environment today, and imagine, what if our cities were planted instead of poured? What if our skylines grew stronger with every storm? Thank you so much for joining me on this explainer, and I really hope it completely changes how you look at the